Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutewa Sos Ukobela Wemets. And without any further ado, let's look at these questions that we have here. Okay, so in today's lesson, we're just going to be having a special session, a revision session for physics, paper 1. So I'll be going through all the topics that you will face in your paper 1 June physics exam. So starting from your Newton's second law, and then we're going to go to VPM, and then we have momentum and impulse, followed by work, energy, and power. And then we have our Doppler effect. We have Coulomb's law, and then lastly, we have electricity. So I believe this is the scope for your June exam, right? So it's gonna be a pretty long video, but then please be patient with me. And then I hope you find this video helpful. Okay, so let's begin. So in question 2, it says we have block A of mass 4.1 kg is connected to block B of mass 2.3 kg by a light inextensible string passing over a frictionless pulley. Then block A is at rest on a rough horizontal table, and block B hangs vertically as shown in the diagram below. Then they say a force F of magnitude 49 Newton is applied on block A at an angle of 50 degrees to the horizontal, causing block A to accelerate to the left from rest along the table. Then they say the coefficient of kinetic friction between the surface and the table and block A is 0.35. So we have new K here of 0.35 between the table and the 4.1 kg block. Then obviously we know this. We always expect that they're going to ask us the definition for Newton's second law. So this is how they expect you to write the definition. So you say Newton's second law states that when an object of mass, when a net force, so when a net force acts on an object of mass, acts on an object of mass, the object will accelerate in the direction of the net force. In the direction of the net force. And then you have to then tell them the relationship. Acceleration is directly proportional to the net force and inversely proportional to the mass of the object, to the mass of the object, right? So this is how you are expected to define it. So do not omit anything as it comes here exactly like that. So you say it states that when a net force acts on an object of mass, the object will accelerate in the direction of the net force, where acceleration is directly proportional to the net force and inversely proportional to the mass of the object. So you make sure you write it exactly like that. Then we have 2.2. It says draw a label free body diagram showing all the forces acting on block A while it accelerates to the left. So now, as we can see, this object is being pulled to the left. So in drawing our free body diagram, we know that we start with the obvious forces. We have our gravitational force, because every object on Earth will obviously experience gravitational force. Then because it is on the surface, we need to have our normal force. And then because there is a rope, we know the tension that is there when there is a rope is tension, right? And then acting opposite to the direction of motion, it's your kinetic frictional force. And always make sure that you draw your tension to be longer than the kinetic frictional force. And then the last one that we have is our applied force. So we're just going to draw it there. And then that's our force applied. Let's indicate FA. Then just like that, that's your 5 marks. So 5 marks, 5 forces. So we have 1, 2, 3, 4, 5. Right. And then 2.3 is saying calculate the magnitude of the kinetic frictional force exerted on block A. Right, so we're going to use our free body diagram. But then the one thing that you always have to note when it comes to calculations is the fact that your free body diagram will be of aid there. So if we want to calculate our kinetic frictional force, we do know the formula for that. It appears in the back of your formula sheet. That's Fk is equals to mu k multiplied by the normal force. Right. But then this is what I want you to observe here. This is a situation whereby your block is being pulled at an angle. So when calculating your normal force should not be equated to Fg only. You have to understand that when we have a diagonal force like this is the force that then resolves into components. Remember, every time a force is applied at an angle, it will resolve to 2 components, namely the horizontal component Fx and the vertical component Fy. Now, in terms of how I figure out the directions for this one, it is simple. If the force applied happens to be in the second quadrant there, then I know the x values for the second quadrant goes in that direction, and the y values, they go up in that direction. So you just kind of imitate what you would have in the second quadrant, your x values that side and your y values that side. And that becomes your fx and your fy. So it is very simple to draw that. So if they were up here, if the force applied was in the first quadrant, then this would be my fy and then fx. If my force applied was here, then this would be fx, and then I would have fy going down like this. Again, if my force applied was in this direction here, this would be fx, and then down here would be fy. So that's just how you draw that. Then up here, we have our fy. Now, that means if we want to calculate the normal force, Fn, this is what we are supposed to do. So you can see from this that every time we are dealing with this, we need to always remember with our vertical forces always balance each other out. So if we say the upward forces are equal to the downward forces, then we do understand that the normal force plus the vertical component must give us Fg, right? And then that means if we want to calculate the normal force, we would have to say Fg minus Fy. This is where we come to the conclusion that every time if an object is pulled at an angle, so every time when we pull an object at an angle, the way we calculate the normal force is always Fg minus Fy. So note this. This is when an object is pulled at an angle. So the way you calculate the normal force, if you see this is being pulled at an angle, is mg minus f sine theta when you then break down this, right? So that means we'll have our mg minus f sine theta, and then let's just substitute. Our mass is the 4.1 multiplied by 9.8, then minus our force applied is 49 is given there, and then sine what? Sine 50 degrees. Then at this point, you just need the aid of your calculator to punch all that. We have 4.1 times 9.8 minus 49 sine 50. Then we have our value as 2.64. So I'll just round off to 2 decimal places and then newtons. But then remember, we are looking for the kinetic frictional force. So now that we have the normal force, Remember, Fn and n is the same thing. That's the normal force. So now I can say Fk is equal to mu k times n. And then remember, I was given the coefficient. Then that's 0.35 multiplied by the normal force is 2.64, right? And then 0.35 times 2.64, that will give us a value of 0.92, right, newtons, right? So it's just like that. So our kinetic frictional force is 0.92 newtons, right? Then, so that's rounded off to 2 decimal places. If we are to round off to 3 decimal places because it's a terminating decimal, let's just say 924 newtons. Okay, so now we have that. Let's now proceed. So 3 marks, just easy like that. Now 2.3.2 is saying, let's calculate the acceleration of block A by applying Newton's second law to each block separately. Now this is how you deal with that. So I will divide the screen here so that I can deal with these 2 objects separately. So pay attention to how I go about solving this one here. Now, the first thing that you need is the free body diagram for both these objects. We've already drawn the free body diagram for block A. So let's draw it again. We have Fg, and then here we had tension, and then also Fk in that direction. And then remember, if we are to draw the one that's resolved, then we have our Fx here, and then up there we have our Fy. Then for the other block here, if this is being pulled or it's being pulled to the left, then we do understand that block B will be accelerating upward. So when we draw, the tension needs to be slightly longer than the gravitational force to indicate that the tension force is larger than the gravitational force. That's why the 2.3 kg block is being pulled upward. So these are the small things that you need to always consider when drawing the free body diagram for this one here. It does matter if it's being pulled up, then the tension is longer than the Fg. But if it was going down, then the Fg would be longer than the tension. But if they were saying this is moving at constant velocity, then your tension would have to be exactly equal to your gravitational force. Because remember, constant velocity means that the upward and the downward force will have to balance each other out. So those are the things you need to consider. Now, when you write there, indicate for block A. So you want to make sure that you detail everything correctly there so that you get your marks deservingly so. So for block A, we have our F net. Remember, when they say by applying Newton's second law, the Newton's second law that we are talking about is this formula here. F net is equal to ma. So we will have Fx minus tension minus Fk is equals to the mass times the acceleration. Now, the one thing that you always have to consider with these questions is that similar to your solve for x in maths, in maths you have your solve for x, your simultaneous equation for x and y. But then in physics, you have your solve for simultaneous equation, and then your 2 unknown variables are your acceleration and your tension. So always when you are dealing with this question, you have to always remind yourself that your tension, you do not have it, and your acceleration, you do not have it. So those 2 are always go hand in hand. If you don't have the acceleration, then you also don't have the tension. Then, okay, because in a system, the 2 things that are equal between these 2 blocks is the tension and the system. So the block A and block B share the same tension and they share the same acceleration. Okay, so dealing with this one, if I break it down, this will be F cos theta and then minus my Fk. So let me just rearrange because I do not have T, and then MA. Now I can just go about substitute and start to substitute here. This is 49 cos 50 degrees. Remember, we did calculate our FK in the previous question. We got 0.924 and then minus T. And then our mass is block A 4.1. So we're 4.1A, right? And then let's now punch this into our calculator. We have 49 cos 50 minus 0.924. And then this is giving us 30.5725. Let me just round off to at least 5 decimal places. Then minus T is equals to 4.1A. Now, if I want to make T the subject of the formula, that's 30.57259 minus 4.1A is equals to T. Then I will call this my equation 1. Then on this other block, I will say for block B, this has to be F net is equals to MA. Now you might be wondering why I said Fx minus T minus Fk. The first thing that I need to do indicate here is that since this block is being pulled to the left, this now becomes my positive direction, and all of this here becomes my negative direction. So which is why you see me saying Fx minus all of this. So the Fx is in the positive direction of motion. Remember, the plus and minus does not depend on what we know with the Cartesian plane. This is not met at that point. So the plus here only indicates that the direction, the positive direction of motion is left. So this object is moving to the left. Therefore, let left be positive and let right be negative. Then here we will have our T. So in that case, this means we have the positive direction here, and then we have the negative direction here. Why? Because as this is moving to the left, remember block B is being pulled upward. So upward becomes the positive direction of motion, and downward becomes the negative direction of motion. So that means we will then have T minus Fg is equals to MA. Now this is my tension. And then what is my Fg? I will say M times G is equals to M times A. Then that's tension minus the mass is 2.3. Remember, now I'm dealing with this block multiplied by 9.8, and then it's equals to 2.3A, right? Now, when I punch that, remember to even include that negative there. So negative 2.3 times 9.8. So we will have T minus 22.54 is equals to 2.3A. Now again, if I want to make T the subject of the formula, that's T is equals to 2.3A plus 22.54. And then this becomes my equation number 2. Now at this point, we will have to equate equation 1 and equation number 2 because they both have T as the subject of the formula. So now I can say, let me equate equation 1 and equation 2. Right. Now, can start by writing equation 2 and then say 2.3A plus 22.54. It doesn't matter which one you write first, as long as you are equating the two equations. Then 30.57259 minus 4.1 amperes. Now I can take the negative 4.1 over to this side. So everything with variable A to the left-hand side, and everything that is just a constant to the right-hand side. To the left, to the left, to the right, where? Then 2.3 plus 4.1, that's a 6.4A is equals to 30.57259 minus 22.4. So this will give us 8.4 17259. And then if we divide both sides by this 6.4, then our acceleration will be, so we have 8.17259 divided by 6.4. So our acceleration is 1 point. So because that's the final answer, let's round off to 2 decimal places, 1.28 meters per second square, right? So this becomes the solution for our acceleration. Okay, so that's it. Just like that, we have earned ourselves 5 marks. So in other questions, they might ask you to calculate the tension. So if they now want the tension, it's easy. Since now you have the acceleration, you'd have to choose whether you substitute in equation number 1 or 2. But then either way, you'd have to get the same tension value, whether you substitute in equation number 1 or equation number 2. They might be different sometimes because of rounding off, but then you should get round about the same value when you substitute your acceleration into either one of these equations to get your tension. But for this question here specifically, they did not want us to calculate the tension, so we just leave it like that, right? So that's how you'd go about answering that question. And then, okay, let's proceed now. We have another question ahead. So, okay, VPM, vertical projectile motion. They say a hot air balloon moves vertically downwards at a constant velocity of 3.4 meters per second when the balloon is 15 meters above the ground. A small ball is dropped from the balloon, refer to the diagram below, right? So this small ball is dropped from the moving hot air balloon, and this hot air balloon is moving downward. So they say the ball strikes the ground and bounces vertically upwards. The hot air balloon continues to move downward at the same constant velocity. Ignore the effect of air friction acting on the ball. Then they say define free fall. Now, when it comes to this topic, we know that the two definitions that we have to expect, it's either free fall or a projectile. So if they don't ask you free fall, they obviously going to ask what is a projectile. Then, okay, to define free fall, we say free fall is the motion upon which the only force acting on an object is the force of gravity. So, okay, there are many variations as to how you define free fall, but then as long as you have the point that the only force acting on that particular object will be the force of gravity, then it is correct. So free fall is the motion upon which the only force acting on an object is the force of gravity. So that's the main point, to mention that it is a motion, and then to also mention that the only force acting there will be the force of gravity. Okay, so now let's proceed. They say the sketch graph below, not drawn to scale, represents the position of the ball relative to the ground from the time the ball is dropped until the time it reaches the maximum height after the first bounce. Now, from the way our diagram is, we can see that this is a position versus time, and then they took a downward as positive. So remember, I did mention that if you see your graph being drawn from below the x-axis in a position versus time, then that means they took downward as positive. If they draw it above the x-axis, then they took upward as positive. Now in 3.2, they're asking, was the ball in free fall between t1 and t2 seconds? Write down either yes or no. Now between t1 and t2, we know that the ball at that moment, it is on the ground, right? So t1, it's when it strikes the ground, and then t2 is before it leaves the ground. So between that point T1 and T2, we say that your ball is on the ground, and therefore it is not only experiencing the normal force. It is not only experiencing the gravitational force, it is also experiencing the normal force. Excuse me for that. So in 3.2, if we had to indicate the free body diagram of your object there between T1 and T2, this is what we would see. This would be the FG, and then here we would have the normal force. Why do we have the normal force? Because now your object is on the ground. Remember, the T1 and T2 is telling you that there's contact time with the ground, right? So if there's contact time with the ground, then obviously the ground or the surface will have to exert a particular force on that ball, so which is the normal force. So at that point, we cannot say that the acceleration of the ball is 9.8 meters per second square, because now it is not only experiencing the gravitational force. So that means at that point, it is not in free fall. So our answer here has to be no. No. Okay, so 3.3, it says use only equations of motion to calculate the value of T1 indicated on the graph. So what is T1? T1 is the time it takes the ball to move from a height of 15 meters above the ground all the way to the ground. But then the tricky part with your hot air balloon questions is the fact that you need to understand Newton's first law. So when reading here, we can see that they told us that a small ball is dropped from the balloon. Now, we would be quick to assume that, that means the VI of the balloon is 0. But then if we assume that the VI of the ball is 0, then this is totally incorrect. Why? Because when the ball is dropped, it was inside a moving object, which is the hot air balloon. According to our Newton first law, we know that if you are inside a car that is moving at 100 meters per second, even if you are seated stationary on that car, you are also moving at 100 meters per second, because anything that happens there when the driver slams the brakes, what happens? You continue in that state of uniform motion. So which means that you were not stationary per se. You were moving along with the car, just that you are not the one that is running or speeding up. But then in the sense that you are inside that moving object, that means you also acquire the velocity of that particular object. So I hope that makes sense. So that means our VI here, even though they say the ball is dropped, it is not 0. The VI is 3.4 meters per second. So that means the velocity of the balloon there becomes the velocity initially of the ball, right? So the velocity of the balloon becomes the velocity initial of the ball. That's what you need to know when it comes to tackling your hot air balloon questions in VPM. Right, so this is 3 marks. So the only tricky part was the VI. If you have assumed it's 0, then you'd be incorrect. If you had understood the concept, V balloon is equal to V ball initially, then you would have the correct answer. Then 3.3.1, the formula that we can use for that one. So let me take you through how I select a formula, because I get a lot of confusion from learners saying, I don't know what formula to choose because there is just a lot of formulas to choose from. Now, this is the rule of thumbs, guys. So we have all these 4 formulas here, like that. And then we also have this. So you don't have to memorize them like I did. They always appear in your formula sheet. I did not really memorize them. It's just practice. Then, okay, now we are looking for the value of T, which is delta T. So the first thing that I will do is I will try to collect the data. So my VI would have to be 3.4 meters per second. And then if I'm taking downward as positive, my acceleration is positive, 9.8 meters per second square. Don't forget that. And then what else? The delta Y is 15 meters. So it's positive as well, because the ball is moving downward, and also I took downward as positive. So the two positions are in agreement. Then what am I looking for? I'm looking for delta T. But then what else don't I have? I don't have VF, because remember there are 5 quantities that we are dealing with: VI, VF, acceleration delta Y, and delta T. So I do not have delta T that time, and then also I do not have VF. But then looking at the question is not looking for VF. So if it's not looking for VF, I will just cross VF. And then that means from the 4 formulas that I have here, I would have to cancel any formula that has VF, because I'm not looking for VF. So this is just the elimination method that will have you end up with the formula that you have to use. So this is a VF. So where there is VF, I will just cancel off. I don't want to use this formula because I'm not looking for VF. I do not want to use this formula also because I'm not looking for VF. I do not want to use this formula because I'm not looking for VF. So where I see VF, I just cross off those formulas. Then obviously from this, we can see that I only end up with one formula to use. That's the correct formula that you should use. So apply that method. When it comes to choosing the formula, apply that method. Then delta Y is equals to VI delta T plus half A delta T square. Now, what's my initial velocity? It's not 0, it's 3.4. I'm looking for delta T, so I'm just going to leave it like that. Then here I have 9.8, then delta T square. Remember, my delta Y is 15, so it's positive like that. And then here I will have 4.9 delta T square, then plus 3.4 delta T. Then if I transpose the 15 over to this side, that's minus 15 equal to 0. Now at this point, we can see that we need to apply the quadratic formula. So quadratic formula from this point, because we can see that it is in a quadratic form. So you already know your quadratic formula. That's you'll say delta T is negative B plus minus, and then B squared minus 4AC over 2A. Then you just go ahead and substitute into that formula. So I'll just punch it into my calculator. Then it's 3.4 plus 3.4 square minus 4. My A is 4.9. My C is negative 15. And then 2 times A, my A is 4.9. Then I have my delta T, the first one, as 1.44 seconds, rounded off to 2 decimal places. Then let me check the other one. So usually you would have one that is negative and then one that is positive. So the one that is negative, obviously you have to cancel it out, because remember, time is a scalar, so it cannot be a negative there, right? So you cannot say you have negative time. So with this one, we say it's not applicable, or you just go here and cancel it out. Then we are left with our delta T being 1.44 seconds. So that's the time indicated in T1. So we'll say therefore T1 is 1.44 seconds. Right, so 3 marks for that. Then let's proceed. Let's proceed. Okay, so 3.3.2 says the height of the hot air balloon above the ground at the instant when the ball strikes the ground. So they want the height of the hot air balloon above the ground at the instant when the ball strikes the ground. Okay, so now remember when the ball was thrown downward here and then reached the ground after 1.44 seconds. Also, your hot air balloon was moving downward at a what? Constant velocity, right? So constant, they said it here, constant velocity. Now we do understand that constant velocity means that the acceleration is 0 meters per second square, right? Remember, when it comes to your hot air balloon is not a projectile. The only thing that is a projectile there is the ball. The hot air balloon is not a projectile. It is not free falling, right? It is moving at its own constant velocity of 0 meters per second square, right? Then there was this particular question where they asked that, is the hot air balloon in free fall? That's a no, a big no. So the hot air balloon will never be in free fall because there are so many forces that are acting there. For the hot air balloon to be able to move, there is some kind of an engine there or a motor or something that propels it. So it cannot be in free fall. Then 3.3.2, the hot air balloon. So what we're going to do now, we are looking for what? The height, right? If we are looking for the height again, let's collect our data. Our acceleration already is 0 meters per second square. Then our VI is 3.4 meters per second. Then do we have VF? No. And then we are looking for delta Y. So we don't have VF. We are looking for delta Y. Then what else? Our delta T, we're going to be using the time that it takes the ball to strike the ground because they're looking for the height of the hot air balloon at the moment when the ball strikes the ground. So that's the time. Now, again, using that strategy of elimination, if we have all our formulas like this, we have all our formulas like that. Then delta Y VI delta T plus half A delta T square. Then we have VI plus VF over 2 delta T. Again, here we are looking for delta Y, but then we are not looking for VF. So all the formulas with VF, I do not want them. So obviously, this will land me with the same formula that I used before. So my delta Y is equals to VI delta T plus half A delta T square. Now, what is my VI? That will be 3.4. And then what is delta T? I will use 1.44, then plus half. My acceleration, note, is not 9.8, it's 0. Then my delta T, again 1.44, and then square. Now, obviously, I know that this part here will just give me 0 because I'll be multiplying with 0 here. So I can just punch this in my calculator. 3.4 times 1.44. And then I find delta Y is 4.896 meters, which if I were to round off to 2 decimal places, that means my height above the ground would have to be 4.90 meters, rounded off to 2 decimal places. Right, so that's how we would go about answering that one there. Okay, so 3.4 says the ball was in contact with the ground for 0.2 seconds. So remember, I did mention that the ball has contact time with the ground there, which means we are looking at an inelastic collision. So guys, always be in the lookout for this question. I always tell you that this question will come whereby they want you to calculate the net force there or something. What do they want us to calculate? Let me read. The ball was in contact with the ground for 0.2 seconds and left the ground with a vertical upward velocity of 7.2 meters per second. Use only equations of motion to calculate the value of T3, also the value of T3 indicated on the graph. Okay, so they said it left the ground with an upward velocity of 7.2. Right, so that's a giveaway. So that means at this time here at T2, the 7.2 here, if they say this is the velocity in which it left the ground, we know at T1, this would be the velocity at which it hits the ground. So remember, at T1, it hits the ground. At T2, it leaves the ground. Right, understand that. T1, that's when it hits the ground. Then it stays on the ground for some time, gains that contact time for 0.2 seconds, and then immediately it leaves the ground. Now, what are they saying? Use only equations of motion to calculate the value of T3, right? So we must calculate the value of T3. Now, what you need to note is that, remember, we did calculate T1. T1 here was 1.44 seconds. And then if this stayed on the ground for 0.2 seconds, that means what is T2? We're going to say 1.44 plus 0.2. That means by the time it leaves the ground, the time is 1.64 seconds. Make sure that you punch that in your calculator. Do not assume it will be 1.46. You see that it's different. That's not 0.02. It's 0.2. So it makes the difference of 0.2 there, right? So 1.44 and then 0.2 seconds in between, we have 1.64. So I always tell you this, that when it comes to writing your exam, please even punch 1 plus 1 in your calculator. So use only equations of motion to calculate the value of T3 indicated on the graph, right? So now it will be leaving the ground at time 1.64 seconds, which is T2. But then at T3, we do understand that when it bounces there, it reaches its maximum height. So it's there in the statement. The sketch graph below, not drawn to scale, represents the position of the ball relative to the ground from the time the ball is dropped until the time it reaches its maximum height after the first bounce. So this is the first bounce, and then it bounces off the ground, reaches the maximum height. So now we can start collecting our data and then say, okay, our V initial in this case would have to be the 7.2 that they gave us. But this is what I need you to note. This is what I need you to remember. When the ball is now moving vertically upward, remember from the very first point, you chose downward as positive. You chose down as positive. So you need to remember, if I chose down as positive and now my ball is going up, that means my velocity will now have to be what? Negative. And also my delta y would be negative. But then my acceleration would still be positive 9.2 meters per second square, because your acceleration is always positive 9.8 if you choose down as positive. And it is always negative 9.8 if you choose up as positive, irrespective of whether it's going up or down. So the acceleration remains constant based on what direction you choose as positive. But then the V and the delta y, that they depend on what the object is doing. Is the object going up or going down? So now that the object is going up, but you chose down as positive, what you are mainly saying is that if the ball now starts to move to the upward direction, then it's opposing my direction of my positive direction of motion. So hence my V is negative and my delta y will be negative. So that means the way I'll be substituting this 7.2 is negative 7.2. This is where now people start to get wrong because of the directions. So always keep that in mind. Always keep that in mind. I always have my reminder with me to always say, okay, the minute I will say down as positive, I need to always remember if the object is going down. So if the object is going down, then I will have my V as positive. I will have my delta y as positive. Then obviously my acceleration still is 9.8 meters per second square. Now, if it's going up, I need to remind myself again, my V will be negative and my delta y will be negative. So when you write those things, then it becomes easy to remember and always and also to minimize the mistakes that you'd be making there. Okay, so we have our VI. This is our data. We have our VI is negative 7.2 meters per second. Then our acceleration, positive 9.8 meters per second square. Then what are we looking for delta t? So the VF, because they mentioned that it will be reaching the maximum height, we know that it's 0 meters per second, because at the maximum height, the velocity is 0. But at the maximum height, the acceleration is not 0. Now, a lot of people tend to confuse that. You ask them, what will be the acceleration of the ball at the maximum height? And they're quick to say it's 0. Note that I asked, what will be the acceleration? The acceleration will forever be 9.8 meters per second square, downward. It's only the VF that is 0 at the maximum height, or the velocity that is 0 at the maximum height. Then we have our delta Y. Do we have delta Y? We are not told about the delta Y. We don't know the position. They did not indicate any value there. So question mark. But then are we looking for that? No. What are we looking for? We are looking for delta T. So again, using that method, I would have to cancel out any formulas with delta Y, right? So I'm very patient with showing you this, because I know once you understand this concept, then you are through. Once you understand that concept, you do not have to always make mistakes here. You can always score your easy marks here. Then VI delta T plus half A delta T square. And that's delta Y, VI plus VF over 2, and then delta T. Now again, let me use that method. So I have delta Y, it's an unknown, and delta T is an unknown, but I'm not looking for delta Y, I'm looking for delta T. So that means I will go there and start to cancel out any formula that has delta Y. So you have delta Y, I won't be using you. You have delta Y, I won't be using you. You have delta Y, I won't be using you. So that leaves us with one formula. So you don't have to be confused when it gets to that. Now you know that's for sure. That's the formula you should use. Instead of just trying to guess which formula you'll end up with here, you now know that you eliminate all the noise, and then you are left with the one that's correct. Then VF is equal to VI plus A delta T. Your VF, that's 0. So it's just plug and play now from whatever the data that you have. VI, remember, negative 7.2. Then my acceleration is 9.8. And then I'm looking for delta T. So when I take this one and transpose it over to that side, that's 7.2 and then 9.8 delta T. Now you see how substituting this as a negative helped me to get my delta T as a positive. Now if you just put it as 7.2 here, you'd soon realize that if you have to transpose, it becomes negative. And then when you try to calculate your time, it becomes negative, which doesn't make sense. And then now you'd be out there trying to be MacGyver and Kenny King the answers. You are Kenny King. Then delta T, we have 7.2 divided by 9.8, which is 0.73 seconds. Okay, but then you have to remember this is a number line, right? This is a number line. And then you can't leave your delta T there as 0.73 seconds. And then remember in T1, you just calculated 1.44. It doesn't make sense that T3 will be 0.73. And then you have this here as 1.44. In the sense of a number line, it doesn't make sense. Now you have to note that the 0.73 seconds here only indicated the time from T2 to T3. But then if you want to indicate the numerical value of T3, then you have to consider this. So this is where a lot of people then miss that mark. So you have to then consider this. So let me try to draw that. So that's 1.44, remember? And then we said it stayed on the ground for 0.2 seconds, which meant our T2 was now 1.64. But then the time it took for it to reach time T3 was 0.73. So the time from here to here is 0.73, which means if we are looking for T3, we need to take 0.73 seconds, add it to the 1.64 seconds. Now the 1.64 seconds, we do understand that we got it from adding the 0.2 here. And then now let's go 0.73 plus 1.64. This is 2.37 seconds, and that becomes your time T3. Right. That's how you were just supposed to go about answering this question here. Easy peasy. Lemon squeezy. Okay, so now we have question 4. It says the two trolleys A and B of mass 3.2 kg and 2.6 kg respectively are held at rest of a stationary horizontal frictionless track with a compressed spring between them, as shown in the diagram below. Now we can see this is what is going on here. So they were both held stationary. After the trolleys are released, the spring extends to its natural length and then falls onto the track. Trolley A now moves with a constant velocity of 0.4 meters per second to the left. Note that, right? So whenever you see to the left, you know that you now have to substitute that velocity as a negative. While trolley B moves with a constant unknown velocity to the right, so it's unknown. Trolley B reaches the end of the track after 1.3 seconds. Then we can see all of that. 4.1 says, state the principle of conservation of linear momentum in width. So quickly, say it states that the total linear momentum in an isolated system is conserved. Now, others might say it remains the same. That's one and the same thing. So these are the definitions you have to look out for. Principle of conservation of linear momentum. They might ask you to explain what is an isolated system. They might ask you to define a momentum. They might ask you to define impulse. They might ask you to define or to explain what is meant by elastic collision and inelastic collision. So make sure that you pay attention to those before you go into your exam. Then 4.3 says calculate the distance traveled by trolley B in 1.3 seconds. And this is 5 marks. Now understand the nature of a 5-mark question, guys. 5-mark question means that you have two unknowns, right? You are looking for the distance, but before you get to the distance, there's something that you have to solve first. Now we can say that the distance can easily be calculated by saying delta x is equals to the velocity minus delta t. But then what is the problem now with trolley B? Is the fact that they said for trolley B, we have an unknown velocity, right? So you see where we get that. So we have an unknown velocity, meaning the first thing that we have to do is to try and find that velocity. Then from finding the velocity, that's when we can then calculate the distance. So, okay, so we have 4.2. Obviously, we're dealing with principle of conservation of linear momentum. So the way we'll be finding that velocity is by applying sum of momentum initially is equals to sum of momentum finally, right? Then this is what I refer to as case number 3, whereby the objects were moving together as a unit and then they separated after collision. As we are told here, the two trolleys were held together stationary as a unit, but then after the spring decompresses, then now we have the two trolleys moving individually in opposite directions. So that means we're going to start with M1 plus M2 and then VI initially. Understand that. That's the only thing that you have to understand. Then M1, V1 finally plus M2, V2 finally. So I'm taking my M1 as trolley A and M2 as trolley B. Then I will have the combined mass here, 3.2 plus 2.6. The initial velocity that they share is 0. And then here I have mass 1 is 3.2. And then they said the velocity of trolley A is 0.4, but to the left. So I need to substitute negative 0.4. Note that. Then here I have 2.6 multiplied by the VF. Now I will have 0 here. And then if I multiply that, that's 3.2 times negative 0.4. I'm getting a negative 1.28, then plus 2.6 VF. Now at this point, we know transpose that, it becomes a positive, then 2.6 VF. Divide both sides by 2.6, then my final velocity becomes 0.49. So we have 0.49 meters per second, but to which direction? Right. At this point, now I can calculate the distance. So to find the distance, it's the V multiplied by the delta T. The V is 0.49. And then they told us that it covers or it reaches the end of the track after 1.3 seconds. So this was moving for a duration of 1.3 seconds. Then let's multiply by that. So 0.49 multiplied by 1.3. Then we find our distance as 0.247 meters, which if we are to round off to the 2 decimal places, it is approximately 0.25 meters. So, okay, that's how we go about tackling that one, guys. Okay. It should be, excuse me for that. I think I made a mistake here. So this is supposed to be 0.63637. I don't know what I did with my calculator, punched it incorrectly. So guys, always note that every time you double check your answers, because instead of pressing 0.49, I pressed 0.19, and then I ended up with that. So that's 0.6364 if we round off to 2 decimal places. So that should be a reminder to you that as much as I make mistakes, you can also make mistakes, but then you need to be very careful, because you making a mistake means that you are losing a mark. So you have to double check your answers there. Now, we have the average force exerted by the extended spring on each trolley while they were in contact with the spring was 4.2 newtons. And then 4.3 says calculate the time it took the spring to extend to its natural length. Right. So now let's read the average force exerted by the extended spring on each trolley while they were in contact with the spring was 4.2 newtons. Note that this 4.2 newtons is not for this collective. It's for each spring. So trolley A experienced a force of 4.2 newtons due to the spring. Trolley B also experienced a force of 4.2 newtons due to the spring. Now, always consider this. You do not use the combined masses when calculating using this formula here. F net delta T is equals to change in P. So this is the impulse momentum theorem, right? So which means that the impulse of an object will be equal to the object's change in momentum. Now we are already given the F net. This is where we need to decide. Are we calculating using trolley A or are we calculating using trolley B? You cannot calculate using the combined masses, because as soon as the spring breaks, then they no longer have the same velocities. So this one ends up with a velocity of 0.4, and this one here ends up with a velocity of 0.49. It's not the same. So you cannot calculate using the combined mass. This is where you need to decide. From calculating using trolley A, then my F net, note the spring here will be exerting a force to the left of trolley A, which is why after the spring decompresses, what happens? Trolley A moves to the left. Now, if it moves to the left, you need to indicate your 4.2 as negative. So you'll have negative 4.2 and then delta T. Now, if you further break this one down, that's M VF minus VI. Now you have the negative 4.2 delta T, the mass for trolley A, that's 3.2. The velocity finally for trolley A, after it has been released there, it's negative 0.4. Why negative? Again, because it's going to the left. So final velocity is negative and also the F net is negative. Remember, the object will move in the direction of the net force. Then the VI is 0. Now, if we calculate that, we have 4.2 delta T. This here, 3.2 multiplied by the negative 0.4. It's going to give us, again, the negative 1.28. If we divide by negative 4.2, negative 4.2, now you see that my delta time will be positive. So I end up with 0.30 seconds. Now, someone might argue, what if I calculate using trolley B? If you use trolley B, you have to understand that the net force now will be acting to the right, because now the spring will be exerting a force directed to the right of trolley B, which is why trolley B then moves to the right. So F net delta T is equal to change in P. Again, you substitute your 4.2 here, delta T. Then if you further break this one down, that's how it goes. Then you have your positive 4.2 delta T. The mass that we have now is 2.6. The final velocity is positive, meant to say, because it's going to the right. We calculated it, it was 0.49, then minus 0. Again, let's calculate 2.6 times 0.49. We are getting 4.2 delta T will be equals to 1.274. And then if we divide both sides by 4.2 like that, then it should be round about the same answer. So 0.30, yes, 0.30 seconds. Right. So whether you use trolley A or you use trolley B, you should end up with the same time. But then always remember, do not use combined masses, because they are saying that the 4.2 Newton is experienced by each block, each trolley, meant to say. So it's experienced by each trolley. So it takes 0.30 seconds for the spring to extend to its natural length. That's how you were supposed to calculate that. Now, trolley B is now replaced by trolley C, which has a larger mass. The same compressed spring is placed between trolleys A and C. The trolleys are then released. The average force exerted by the extended spring on the trolleys remain at 4.2 Newton for the same period of time as calculated in question 4.3. How does the magnitude of the velocity of trolley C compare to the magnitude of the velocity of trolley B after the spring has fallen to the track? Right? Only greater than, less than, or equal to. Right? So now they're asking about the velocity. So how does the magnitude of the velocity of trolley C? Remember, they said trolley C has a larger mass, right? So if trolley C has a larger mass, then we do understand that the one with the larger mass will have to have a smaller velocity, because the relationship between mass and velocity, so according to P is equals to M times V, we know that the relationship between mass and velocity is inversely proportional. So the bigger the mass, the smaller the velocity. So in answering that one, we would have to say the velocity will have to be less than. Then we say, according to P is equal to M times V, M is inversely proportional to velocity for a constant momentum. So that means the greater the mass, the smaller the velocity. The smaller the velocity. So this was just based on the relationship. Should be less than, because the greater the mass, the smaller the velocity. Okay. Now, let's get to question 5. Question 5 says a crate of mass 18 kg initially at rest slides down a frictionless slope from point A to point B. The crate then moves along a rough horizontal surface from point B towards point C. Then they say point A is 3 meters above the horizontal surface. See the diagram below. Then we have our definition there. Says state the principle of conservation of mechanical energy. Then let's start with that one. So we'll say it states that the total mechanical energy in an isolated system is conserved. In an isolated system is conserved. Right. Now, when it comes to the definitions, you should expect that's your principle of conservation of mechanical energy under work energy and power. Then you also have the definition for power. They might ask you to define the work energy theorem, which we can even see it here. They might ask you to define or differentiate between a non-conservative force and a conservative force. So also those are some of the definitions you should be on the lookout for. Then 5.2, they say using energy principles only, calculate the speed of the crate at point B. Now, if they're saying we must use the energy principles, that means we can use either the mechanical energy, principle of conservation of mechanical energy, because these are your energy principles. Principle of conservation of mechanical energy, which says sum of EM at A is equals to sum of EM at B. But then you only use this one if the surface is frictionless. So here there is no friction. Make sure when you read that they're telling you that on that particular area or on that particular displacement, there is no friction. Then number 2, we have WNC is equals to change in EK plus change in EP, which is the work done by non-conservative forces. So you use this one if you can identify non-conservative forces. Your non-conservative forces, remember, can be your force applied, your tension force, and your frictional force. Then we have number 3, W net is equals to change in EK. This one is pretty much neutral. You can use it anywhere, but then I prefer that you use these ones on horizontal surfaces, right? So, but then either way, it is neutral to any situation, whether there is friction or no friction, whether there are non-conservative forces or no non-conservative forces. So, okay, now use the energy principle to calculate the velocity of B. Let's read here. They say a crate of 18 kg initially at rest slides down a frictionless slope. That's the keyword that we need. Frictionless slope. The minute they tell us that the slope is frictionless, then we know. Without any further question, we just go and choose that one. Sum of mechanical energy at point A will be equal to the sum of mechanical energy at point B. Now remember, mechanical energy is the sum of the object's potential energy and kinetic energy. So that means we will have mgh at A plus half mv squared at A. Now remember that the V has a square here. That's energy. Then also we have mgh at B plus half mv squared at B. Now it's all just a matter of substituting in your values. Your mass, you have 18. The gravitational acceleration, always 9.8. The height at point A, that's 3 meters above the ground, so 3 here. And then half, again, we have the 18. So this is 18, guys. And then V, the velocity at that point, remember they said initially at rest. So if it's initially at rest, that's 0. So 0 square. My mass again 18, and then here 9.8. But the height at B, when it reaches B, it's now on the ground, so there's no relative height. That's 0. Then I have half. My mass is 18, and then I'm looking for this V squared at B. Now it's just a matter of punching into your calculator. Obviously, this one will give me 0, so I'll only punch this part. 18 times 9.8 times 3, that's giving me 529,2. And then half of 18, that's 9, so we have 9. And then V squared B, divide by 9 both sides. Then we have V squared B is equals to 529.2 divided by 9. That's 58.8. But do not be carried away. We still have the square. So that means we have to square both sides like this. Then the velocity at B will then be 7.67 rounded off to 2 decimal places. Meters per second. Right. So 7.67 meters per second. That's the speed at point B. Right. So let's write it somewhere. Then let's proceed now. They say a constant frictional force of 40.6 Newton acts on the crate as it moves from point B towards point C. The crate comes to rest at point C. The crate comes to rest at point C. Now 5.3 is saying state the work energy theorem in words. So we say states that the net work done on an object is equal to the object's change in kinetic energy. So the work energy theorem states that the net work done on an object is equal to the object's change in kinetic energy. Right. Then 5.4 says using energy principles only, calculate the distance that the crate traveled from point B to point C. Now remember what I just said regarding the energy principles. I said if we are now on a horizontal surface, I prefer to use W net. Right. You can also use WNC given the fact that you are given that a constant frictional force of 40.6 Newton is acting there, and frictional force happens to be a non-conservative force. Right. NC, non-conservative force. Okay, so now I will just try to calculate this using both the formulas. So starting with W net, for W net, I will just go is equals to change in EK. And then now that we understand when the block comes here, the only force that will be acting there is the kinetic frictional force. Because remember, as the block was sliding here, it was not being pushed by anything. So it's just falling at its own accord and then sliding here at its own accord. So there is no applied force, meaning the only horizontal force, the force that is doing work, is Fk. Remember, we do have the normal force and then we do have the Fg, but the normal force and Fg are not doing any work on the object because they're acting perpendicular to the displacement, right? So remember, if a force acts perpendicular to the displacement, then it does no work. The work is 0 joules. So that means the only force that will be doing work is the kinetic frictional force. So to calculate that, we'll say the W net is only represented by WFK, and then which will be equal to change in EK. And then to further break down this one, this is Fk delta x cos theta, because what am I looking for? I'm looking for this delta x here. So that's why I'm breaking it down. So if you are either looking for delta x or you are looking for theta, or you are looking for the value of Fk, then you have to break down that formula, because we are not calculating the work done. We are trying to calculate something else. Then let's break down also this part of the formula, half m Vf squared minus Vi squared. Now my Fk, they told me it's 40.6. So I have 40.6 multiplied by the delta x cos. Now the theta here, remember that your frictional force is always opposing the motion of the object. Looking at this, we can see that the angle that will be formed between the displacement and the kinetic frictional force will be the angle in between a straight line, which is 180 degrees. Remember, always with Fk, because it is opposing the displacement, we will always have to substitute 180 for the theta there. Always. When you put Fk, then just know you put 180 there. And then half, our mass is 18. And then what are we trying to calculate? They said, calculate the distance that the crate moves. So until it comes, the crate comes to rest at point C. So final velocity will be 0, but initial velocity will have to be the velocity at point B, which we did calculate at 7.67 square, right? Then calculating here, we have negative 40.6 and then delta x. If we punch all this into our calculator, that's 1/2 multiplied by 18 multiplied by 0 square minus 7.67 square. So the way it appears there, punch it like that. So 529.4601. We divide both sides by negative 40.6, negative 40.6. Then our delta x becomes 13.04 meters, right? That's how you would have calculated that one using the work energy theorem. So 13.04 meters. So that's the work energy theorem, right? Now, let's say someone else had chose to use the WNC formula. It will not be any different from this one. So work done by non-conservative, you'd say is equals to change in EK plus change in EP, right? And then obviously because here there is no relative height, this would make your change in EP to be 0. So no relative height. So it's moving on a horizontal surface. Now, do you see why it is just as much quick to just use the W net? Because if you use this one, then the change in EP will be 0, which will then lead you to WNC is equals to change in EK, which is the same as just writing W net is equals to change in EK, because the only force that is acting there is that non-conservative force, friction. So it's one and the same thing. You'd then find the same answer from here, because all you would have to do here is say Fk delta x cos theta, and again you break this one the same way we did with the one that we just solved. So also again your delta x would be the same answer. It would be 13.04 meters. So it's one and the same thing. It's one and the same thing, guys. Then 5.5, the height of the track is now lowered so that point A is at a vertical height. So less than 3 meters. So now they're lowering this one. So let's just kind of try to see what they did there. And then how will the distance now travel by the crate along the horizontal surface before it comes to rest compared to the distance calculated in question 5.4, right? Only greater than, smaller than, or equal to. Explain the answer. Now, okay, let's observe this. So now they've lowered this. Let's say now they've lowered it to 2.5. They're saying, how will this affect the distance that it travels here? We do understand that if this is coming from a greater height, then it will garner a lot of potential energy, which when we transfer this potential energy to kinetic energy as it moves, as it slides down here, it will cause the block to cover much more distance on the horizontal surface. But then now when we are lowering the slope, we are causing the potential energy to be low, and therefore when it is now released, the potential energy that will be converted to kinetic energy will be lower, and therefore it will cover a smaller distance. So our solution there has to be less than, smaller than. So smaller than. And then we say with a lower vertical height, the object will have a smaller potential energy, right? And thus a lower kinetic energy at point B, right? And then causing the object to have a smaller velocity. That's covering a lower distance. That's covering a smaller distance. So now I am explaining the fact that from here, it will have a lower potential energy. This potential energy, remember, there is an energy conversion that will be taking place here. This potential energy needs to be converted to kinetic energy. So if we have a smaller potential energy at this point, then we have a smaller kinetic energy at that point. A smaller kinetic energy means that we have a lower velocity, and then a lower velocity means that the distance that will be covered here will be small, right? So that's the whole point here. So that's the whole point. So smaller than, with a lower vertical height, the object will have a smaller potential energy and thus a lower kinetic energy at point B, causing the object to have a smaller velocity, thus covering a smaller distance, right? So I hope that makes sense. We have question 6. It says a stationary listener records the frequency of the sound emitted by the siren of a police car when the car, which is traveling at a constant velocity of 26 meters per second, approaches the listener. The recorded frequency is 615 hertz when the car is approaching. Then the car passes the listener at time t1 and then moves away from the listener. The recorded frequency now is 526 hertz. So when the car was approaching the stationary listener, we could observe the frequency was higher, but then as soon as it moved away from the stationary listener, the frequency was now lower. Then ignore the effects of wind. 6.1 says state the Doppler effect in words, as always expected. So we say a Doppler effect is the apparent change in the frequency of the sound detected by the listener because the listener and the sound source have different velocities. So it's a long one, but then that's how you should define it. Have different velocities relative to the medium of sound propagation, right? And that's how you define Doppler effect. So you say is the apparent change in the frequency of the sound detected by the listener, because the listener and the sound source have different velocities relative to the medium of sound propagation. Then we have 6.2. It says use the information given to calculate the speed of sound in air, right? Now we can see we have two scenarios. So the first one is when it's moving towards. So let me separate here. We have towards and away. So while it's moving towards, this is what happened. So we have our formula. That's FL is equals to V plus minus VL over V plus minus VS. And then that multiplied by Fs, right? So we start with the original formula. And then we can now try to substitute in here to say that we know that our frequency of the listener, when it's moving towards, that's 615. And then if it's moving towards, we say keep the plus upward there and then the minus down here. So if it's towards, we say plus here and then minus down here. So the velocity, that's what we are trying to calculate, the speed of sound in air. So that's V. And then here we have plus the velocity of the listener. Velocity of the listener is 0 because they said it's stationary. Then we have V minus the velocity of the source. That's 26. But then we don't have the frequency of the source. Note that. Now, the trick that I always taught you here, if you want to make Fs the subject of the formula, is just to swap these ones here. So the Fs will be here, but then not only swap these ones, you also need to make the numerator denominator and denominator numerator. So note what is happening here. So in you swapping these ones, you also have to consider that this is what will happen here. So Fs becomes the subject of the formula. Then we have V minus 26 over V and then multiplied by the 615 there. So that's it. At this point now, we can leave it like that, or maybe further continue and say this will be 615 V minus 26 multiplied by 615. This will have to give us 15,990 over V. Let's call this equation number 1. And then if we are to look at away, with away, say the plus will be down here and the minus will be up there. So that's FL is equals to V plus minus VL over V plus minus Vs, and then multiplied by Fs. Our FL, when it's moving away, that's 526. And then we have V minus 0, and then down here V plus. Vs is a velocity of the source, that's 26. Then the frequency of the source we don't have. Again, if we want to make it the subject of the formula, we have Fs, and then this will become V plus 26 over V, and then right here we have the 526. And then Fs is equals to 526 V plus what's 26 times 526? That's 13,676 over V. Now this is equation number 2. Now that we have equation number 1 and equation number 2, and they're both having Fs as the subject of the formula, this is the part where we say now equate equation 1 and equation 2. So we have to equate the two equations. Then allow me to just do it here. So we have 61V minus 15,990 is equals to 526V plus 13,675. Now, I won't be putting the V and V because looking at this, we can see that if they have the same denominator, then we can just cancel off that denominator by multiplying by V both sides. So if you multiply by V here, multiply by V there, then the V and V will cancel out. So we are only left with this linear equation here. Now we can try to bring all those ones with V to one side and all those ones with constant to one side. So that's 615V minus 526V is equals to 13,676 plus 15,990. And then what do we get from subtracting this here? 615 minus 526. That's 89V. And then if we add those ones, 13,676 plus 15,990, that's 29,666. Then dividing by 89 both sides, then the velocity of the speed of sound in air, that becomes 29,666 divided by 89. And then we find that the speed of sound in air is 333.33, rounded off to 2 decimal places, meters per second. And voila, just like that, you have your 5 marks. So that's how you were supposed to calculate that. So, yep. Okay, and then now let's move to 6.3. 6.3, it's saying calculate the wavelength of the sound emitted by the police siren. So calculate the wavelength, right? So to calculate the wavelength, we know the formula goes V is equals to F and then delta, lambda. So obviously we do have the velocity from previously on, but then we don't have the frequency of the source. So remember, to calculate the frequency of the source, now we can go back to one of the equations here and then just choose the one we can use. So we can use either this one here or we can use that one there, right? So let's have our 615V minus 15,990 over V. So we can use equation 1 or equation number 2. Then if we have to use equation number 1, our frequency of the source is equals to 615V minus 15,990 over V. Now in the position of V, we just substitute the value that you got, 333.33 minus 15,990 over 333.33. Now, to find the frequency of the source, let's punch all that. 615 times 33.33 minus 15,990 over 33.33. So this will give us Fs is equals to 567.03, right? And then hertz. Now to calculate the wavelength, we go V is equals to F times lambda. Our V, that's 333.33. Then the frequency we already calculated now, 0.3, and then multiplied by lambda. Now to calculate the lambda, let's divide both sides by this, 567.03. Then lambda is equals to 333.33 divided by 567.03. Then our wavelength becomes 0.587, which is 59 rounded off to 2 decimal places, and then meters. Remember, wavelength is a distance, so it needs to be calculated in meters, 0.59 meters. That's how you could have calculated that. Now, 6.4 says sketch the graph of recorded frequency versus time for the motion of the car as it moved towards the listener, past the listener, and then moved away from the listener. Label T1 on the graph, right? So no values needed to be indicated on the frequency axis. So they're not requiring us to put in the values, just to show the shape of the graph. So starting with your axis there, then here you obviously have your time, and then your time, and then up here, so your time must be in seconds, and then up here you have a frequency, and then it's given in hertz, right? Now what happens is that initially we had, as it was approaching, we had a frequency of 615, and then at T1 we will say this is when the car was now in the same position as the stationary observer, and then from there on what happened, it passed. So now it had a lower frequency, and then just like that. So we are not supposed to indicate any values on the axis. We can just have our 0 there. But if we were indicating values, then this would be the 615 here, and then this would be the 526 here. So all that you are supposed to do is that. So label frequency, label time, then show that T1 is here at the moment where now the car was now at the same position as the stationary listener. Then after point T1, that's when the car now starts moving away from that stationary listener. So that's how you are supposed to indicate that, and then done. Okay, so question 7, that's on Coulomb's law. It says X is a point 0.025 meter away from a positive 4 nanocoulomb point charge. See the diagram below. Then as we can see the diagram there, then 7.1.1 says draw the electric field pattern due to the positive 4 nanocoulomb charge, right? So to draw the electric field pattern due to that, remember the point charge is always a positive, right? So point charge is positive. So in order to draw the electric field pattern due to the 4 nanocoulomb charge, then this means that we would have this. This is a positive, and then also our point charge is a positive. So that means we would have a repulsion electric field pattern here. So it will go like that, go like this, and then like that. Okay. Positive, positive. Let me try to draw it nicely. Having shaky hands, but then yeah, get the whole point. So that's it. So as long as these fill lines will not touch, right? So the fill lines, remember, they should not touch, and then they should come from individual points, right? So there will be no fill lines that are touching or crossing there. And then since it's positive, what's important is to indicate that the charges are outward. So for positive, we say charges are outward. So outward charges, like that. And then just like that, you have now indicated the electric field pattern, right? So that's all that you indicate there. Now 7.1.2 says calculate the magnitude of the electric field at point X. We have to write the formula E is equals to KQ over R squared, right? So that's the formula to calculate the electric field. Then it's only 3 marks. So that means here we substitute our K value, which is always found in the back of your formula sheet. Then your Q needs to be 4 times 10 to the exponent of -9. Remember, nanocoulomb, when you convert nanocoulomb, it converts to times 10 to the exponent of 9. Also remember, macrocoulomb converts to times 10 to the exponent of -6. So very crucial for you to know. And then also another necessary thing that you have to know is that if you are given your distance in centimeters and then you want it in meters, you have to divide by 100. And then if you are given in millimeters and then you want meters, you have to divide by 1000, right? So these are the necessary conversions when it comes to your Coulomb's law. Then what is R? The R is given in meters, so we're just going to substitute 0.025 and then square that, right? So we end up with 57,600 Newton per Coulomb, right? So remember, the SI unit for electric field is Newton per Coulomb, right? So 3 marks like that is the formula, substitution into the formula, and the correct answer. Okay, so 7.2.2, it says calculate the magnitude of the initial charge QB given to ball B if the mass of each ball was 0.012 kg. Then when we go back here, they said ball B is then given an initial negative charge QB of unknown magnitude. The balls attract each other, touch, and then repel each other. Now we know this is the case whereby after they attract each other, they touch and then repel, they will then share the same charge, right? So the charge after contact, the charge in QA is equal to the charge in QB. So let's note that QA will be equal to QB after contact. After contact. Because that's where they get to share the charges, right? So now we want to start this question with the triangle of forces. So this is similar to what we do in grade 11. So we have our gravitational force going like that. And then we have our tension force, as we can see. So the trick here is just to not change any forces. So you put your forces as they are there, then tension. Then again, we know that it will be repelled by A. So this is for ball B, by the way. These are all the forces that are acting on ball B. Then it is experiencing an electrostatic force from A. And then this electrostatic force is being directed to the right of B, right? So we have our 9 degrees here. If we are being told that the balls come to rest, that means this whole system is at equilibrium, meaning our triangle of forces will be a closed vector diagram. Remember, a closed vector diagram only happens if our system is at equilibrium, which is the same case here. We have 9 degrees here, 90 degrees. So that means we must have 81 degrees this side here. Now, obviously, we can start by calculating the electrostatic force here, and then also calculate the gravitational force. So let's start with the gravitational force, by the way. And then our mass here, we are given is 0.012, and then times 9.8. Now our gravitational force is 0.012 times 9.8. 0.012 times 9.8. This will give us a value of 0.1176 newtons. Then, okay, from here, we have the gravitational force. Let's put it here, 0.1176 newtons. And then to calculate the electrostatic force, let's use the triangle here. We have the adjacent side in respect to this 9 degrees that we are given. We have the adjacent side, and then our electrostatic force happens to be the opposite side. Now we know that from that we can use the trig ratio tan theta. So tan theta will be equals to what? So we'll say tan theta will be equals to the opposite side, which is Fe, over the adjacent side, which is Fg. Now that means we have tan 9 degrees will be equals to Fe over the 0.1176 that we found for the gravitational force. Now that means our electrostatic force now needs to be that multiplied by tan 9. It's going to give us 0.0186 newtons. Right. Now at this point, we do understand that if we are to, this is the electrostatic force after they have came to contact and separated. So let's use that to find the charge of B after contact. So we are trying to find the charge on B after contact. After contact. So remember, what we are actually looking for is the initial charge QB. That is before contact. But then since we have the electrostatic force after contact, the first thing that we have to calculate is the charge on B after contact. So that's Q. And then we have QA, QB over R squared. But you will remember that I said QA is equals to QB after contact. So that means I have my 0.0186 here. Then the K, we know it's 9 times 10 to the exponent of 9. Since these ones are equal, we can just say this is QB squared. Because I will have QB multiplied by QB. So that's QB squared. Then the R here, that's 10 centimeter. I cannot substitute 10 centimeter here. Remember, centimeter to meters, we have to divide by what? 100. So 10 divided by 100, I will have to substitute 0.1 square here. Then if I cross multiply this, my QB square is equals to 0.0186 multiplied by the 0.1 square over the 9 times 10 to the exponent of 9, right? So I'm just kind of doing all my math all at once, and then I would have to square both sides like that, and then quickly just punch this into my calculator. Then this is 0.0186 times 0.1 square over 9 times 10 to the exponent of 9. And then all that is inside the square root. So it will give me 1.43 times 10 to the exponent of -7 coulombs. Okay, now that I have that, my QB is that I'm not done, right? You will remember that this is the charge on B after contact, but I'm looking for the charge on B before contact. Now, when I go here, they say these two identical neutral polystyrene balls were neutral, right? So that means they had a charge of 0. But then just before they made them to come into contact, they gave ball B a negative initial charge, right? So B had an initial negative charge. Now, and then QA, they did not do anything to QA. That means QA remained 0, neutral. Remember, neutral means that the charge is 0 coulombs. So that means using this formula, Q nu is equals to QA plus QB over 2. This one that we see here will be representing the Q nu, because that's why QA is equals to QB after contact. So we'll say 1.43 times 10 to the exponent of -7. The QA is 0. But then remember, QB was made to have a negative charge. So I can say this is minus QB. So plus negative QB over 2. Now, when I cross multiply here, this will then give me 2.86 times 10 to the exponent of -7, which is equals to negative QB. If I divide both sides by negative, that's the negative charge that was initially given. So that's negative 2.86 times 10 to the exponent of -7 coulombs, right? So in that way, I have calculated the magnitude of QB that was given, right? So it was negative 2.86 times 10 to the exponent of negative 7 coulombs. And that's how you were supposed to go about calculating that question for 6 marks. So yeah, it was a pretty lengthy question, but then you just needed to understand what needed to be done. Okay, and so now we have question 8, the electric circuit. So it says a battery of EMF 12 volts and internal resistance of 0.2 ohm is connected to 3 resistors, a high resistance voltmeter, and 2 switches. An ammeter and connecting wires of negligible resistance as shown in the circuit diagram below. The 3 resistors have different and unknown resistors. And then we are told that the resistance of Ry is twice the resistance of Rx. So that means Ry can be indicated as 2 times Rx, right? And then when both switches are closed, so meaning as we can see here, when both switches are closed, the reading on the ammeter is 5.5 amperes. And then the first question is asking, give a reason why there is no current through resistor Rz. Now, what you need to observe here is that if your current is flowing in this direction, flows all the way like that, reaches this parallel branch here, and then decides to flow like that, and then meets up in this position here. But then what happens is that as it meets up here, now you can see that instead of having to choose to go to this direction, it then now goes to this direction here, because remember, this is a connecting wire, and the connecting wire has the lowest resistance. Then your charges always want to go to the path of lower resistance. So what we have done here is a concept known as short circuiting, whereby now we put a wire there and the wire will be diverting all that current through it, right? So all the current will be flowing through this connecting wire of lower resistance, and therefore no current will be left to flow to the RZ. So in explaining that, we just say all current flows through the connecting wire, with very low resistance. Thus, no current flows in resistor RZ. So we say all current flows through the connecting wire with very low resistance, thus no current flows in resistor RZ. So that's what happens here. It's a case whereby this is known as a short circuit. So a short circuit is a faulty connection, whereby now we introduce a connecting wire of a very low resistance, which will be taking all of the current and then leaving the other parts of the circuit not to receive any current. Right, so let's proceed. Now we have 8.2. It says, calculate the resistance of resistor Ry. Right, so we are given this, and then to calculate that, we can say 8.2. Let's start with the formula. EMF meant to say is I R externally plus R internal. The EMF, we can see we are given here, it's the 12 volts, and then the I there, which is the current, we are told it was 5.5, right? Then we are looking for the R external, then plus the internal resistance is 0.2. Then to calculate here, we can divide both sides by this 5.5, and then we'll have 2.18 rounded off to 2 decimal places, then R external plus 0.2. Now, if we take the 0.2 over to the side, then our R external ends up becoming 1.98 ohms. So this is the total resistance, but then remember, we are interested in the value of Ry. Remember, we just said that in Rx, current is not flowing. So this connection here, we pretend as if it's not there. So the only resistors that are making the R external is the Rx and the Ry resistor. So meaning to calculate the value of Ry, remember we said that Ry can be expressed as 2Rx since it's twice the resistance of Rx. Now if we use product over sum, which is, we will have to say Ry. So if we use the product over sum, this will be Rx plus Ry over, so that's Rx times product over sum. So it's a product, and then here, down here, we have the sum. So product over sum is equals to the R external, right? Then this will now be what? Rx. Remember, the Ry can be expressed as 2Rx. And then here we have Rx plus 2Rx. Why do I keep on putting a plus here instead of multiply? So that's times. And then this one is 1.98. Okay, so when we multiply the 2 here above, Rx times 2Rx, this will have to give me 2Rx square. And then below we will have 2Rx. And then this is equivalent to 1.98. Now, when we continue solving this there are 2 Rx here, and then there's 1 Rx. So this will leave us with 2 Rx. Then the 1 Rx will divide with that one over 3 is equals to 1.98. Now, if we cross multiply here, that's 2 times Rx. What's 3 times 1.98? That's supposed to be giving us 5.94. Now, if you can look here, the 2 times Rx represents Ry. So we can say, therefore, Ry is equals to 5.94 ohms. Because remember, we said twice the size of Rx is equals to Ry. So we just got 2 times Rx is equals to 5.94. That means our Ry is 5.94. So for 5 marks, that's just how we were supposed to calculate that. So note that here we have multiply, and then down here it's a plus. So multiply here, and then down here it's a plus. Okay, so just like that, we have calculated the resistance of Ry. Then 8.3 now says calculate the power dissipated by the resistor Rx. Now, we know the formulas to calculate power, either I squared multiplied by R, P, V squared over R, or P is equals to V times I, right? Now, obviously, because these two resistors are connected in parallel, and what we know about parallel resistors is that they have the same voltage throughout, then we can all agree that it is best for us to use the voltage and the resistance. So equation number 2 would be the perfect one. But then the question is, what is the voltage there, right? Now, how would we calculate the voltage in there? Remember, we already have the RP, or the resistance of the parallel. So we can say to calculate the voltage in the parallel, that's the current multiplied by the resistance in the parallel. Or as we know it, is the external resistance, since these are the only two. Now, Vp is equals to our current is still 5.5, but then the total resistance that we calculated, we found that it was 1.98 from the previous question when we calculated R external. So R external, remember, we got 1.98 ohms. So this is the same RP. Now, when we calculate the voltage in the parallel, we find that it is 10.89 volts. Now, we want to calculate the power dissipated in resistor Rx. Remember, we just calculated Ry, and then we said that Ry was 5.94 ohms. Now, Ry, we were told that it is twice Rx. Then that means Rx has to be half of this. Then 5.94 divided by 2. If Ry is twice Rx, then that means Rx is half of Ry. Then we find that it is 2.97 ohms. Right. So now at this point, we can now calculate the power. We're going to say power is equals to V squared over R. And then what is our V? That's the 10.89. And then square. And then the R is the 2.97. Now, if you punch that into your calculator, your power is now 39.93 watts. Right. That's how you would calculate that. So for 4 marks, you have calculated the power dissipated by resistor Rx. Okay, so when both switches are now opened, so that means they're opening up S2, and then they also open S1. Now note that when they open S1, this current that was now flowing here will no longer be flowing in that direction, will now continue flowing in this direction here. So that means when they open switch S1, current starts to flow in resistor RZ. Note that. But when they open up switch S2, the current will only flow in resistor RY, and it will not flow in resistor RX. So now when they open switch S2, in RX, there is no current. So there is current in RY, and also there is current in RZ. Now, 8.4 says calculate the reading on the voltmeter. They said when both switches are now open, the reading on the ammeter is 1.3 amperes. So for 3 marks to calculate that one, it should be easy. Should say V is equals to I of resistor Y, and then multiplied by R of resistor Y. Now, what is the current in resistor Y? Since these two resistors will be connected in series, we now know that this one will read a current of 1.3 amperes, but also that one will read a current of 1.3 amperes, which is the same 1.3 amperes that will appear here. So remember, when resistors are now connected in series, we say the current is the same throughout. Then now we have 1.3 here, then multiplied by the resistance of resistor Y, which is, we did calculate in the previous question, it's 5.94, right? Now, multiplying this two, we will find our voltage is 7.722 volts. So 7.722 volts, that becomes the reading on the voltmeter. This voltmeter here. So this voltmeter here will be reading the voltage flowing in RY. Now, switch S1 remains open while switch S2 is now closed. Right. I want you to note that. So now they're saying switch S1 remains open while switch S2 is now closed. So this is the scenario that takes place here. So switch S1 remains open, meaning they're still allowing current to move in RZ, but now they close switch S2, meaning they now introducing RX back. So RX current is flowing here, and then also in RY current is flowing. Now you can see that we have RX, RY, and RZ now in play, right? So if we want to calculate the reading on the ammeter, we should calculate the reading, the ammeter reading when all these resistors are now receiving current. Right. And now how do we do that? Now we can see the trace mesh is that we do not know the value for RZ, right? We do not know the resistance of RZ. But then if we are to go back to when both switches were open, so let's say with both switches open, this is how we would find the reading of RZ. So with both switches open, we would say EMF is equals to the current and then R external plus R, right? The EMF, remember, it does not change. It's 12. It will forever be 12 because the EMF is the EMF of the battery, right? So this is the total potential difference. So it will never change. It always remains like that. So two things that never change is the EMF and the internal resistance. Whether you choose to close or you open switches, the EMF remains the same because this is the total potential difference when no current is flowing, meaning that it is the potential difference of the battery itself. Then we are looking for remember this is when both switches were open. So they said when both switches were open, the current was 1.3. So let's say 1.3 here. And then we have R external, and then R internal, always 0.2. So if we divide both sides by this 1.3, then we find that 12 divided by the 1.3 will give us 9.23. And then this is R external plus 0.2. Now the R external can be calculated by saying 9.23 minus 0.2, and then we get 9.03 ohms. Now, what is this? This becomes the R external when both switches are open. So that means, considering that when both switches were open, the only resistors that were in play was RY and RZ, then we can say the R external is being represented by RY plus RZ. Now, if the R external is 9.03, and then we calculated the RY to be 5.94, then what is the value for RZ? Now RZ will just become 9.03 minus 5.94, which makes our RZ to be equal to 3.09 ohms. Right. So remember, the resistance of the resistors do not change. The resistance of the resistors will always be constant like that. So whether you choose to put in more current there, the resistance is the resistance of that particular resistor. Now we have the RZ there. It's 3.09 ohms. So I want us to now go back to the question that we are trying to answer here. So remember the RZ, that's 2.97 ohms. And then here we had 5.94 ohms. Now we got that this one is 3.09 ohms. Right. So that means let's go back to when S1 is open and S2 is closed. So now we are trying to calculate the current when S1 is open and S2 is closed. Mind you, it won't be the same current. It won't be the 1.3 amperes because remember, we just introduced another resistor here, Rx. Right. So we just introduced the resistor that is now connected in parallel. Now, if the resistor is connected in parallel, we know that the total resistance will decrease and therefore the total current must increase. So the answer that we are expecting to get must be higher than 1.3 amperes. So again, we have EMF. So before we do the EMF formula, let's now figure out what will be our R external. Our R external for when S1 is open and S2 is closed will now be the 1.98 ohms from the parallel resistors plus the 3.09 from the resistor that is connected in series. Remember, your R external is resistors in parallel plus resistors in series. So when we add the two, we get 5.07 ohms. Right. So this is also crucial that you show. Then to calculate the current, we go back EMF, current, R external plus R internal. The EMF remains the same, still the 12. The current, that's what we are trying to find. R external, that's what we just got here from adding the ones in a parallel, which gave us 1.98. plus the one in series, that's 3.09. Remember, you don't add like this, right? You calculate these ones using that formula, which we did, and then plus that. Then 5.07 plus 0.2. So that's 12 here. And then we have, when we add these ones together, that's 5.27. We divide both sides by 5.27. Then what is our current? Our current should be 2.28, which confirms our observation. We know that when we connect a resistor in parallel, the current should increase, right? So comparing when both switches were open, we only had 1.3 amperes. But now when we leave S1 open and then S2 closed, then this now becomes 2.28 amperes, right? So that's how you were supposed to calculate the current there for 6 marks. And then all of this question here for 19 marks. And then just like that, we've came to the end of the lesson. We've done all the topics that you're gonna find in your paper 1 June exam physics. So make sure you play this video and just try to practice along with me. Don't just watch the video and look at the answers that I'm getting there. Try to also solve them while you are watching the video and pause while you are doing the questions. Then check your work against mine. Then all the best, guys.